Okay, so let's look at this problem. Let me zoom out a little bit. I'm a little close. A little bit more. That'll do it. So the problem, as originally defined, was to draw the shear force and bending moment diagram. And just to review, with this linear load, we know that the shear diagram is going to be quadratic, and the graphical approach for that, although not impossible, is a little more tedious. You have to have either knowledge in your memory of areas of parabolic sections and centroids, or you'd have to be provided that data. So as an alternate to that, I think it would be better to quickly write the shear force and bending moment equations, and then from those equations we might be able to derive maximum moment, maximum shear. So as a different approach, we'll do that. So let's imagine the structure being cut at some distance x. And let's just review quickly whether you want to work the left side or the right side of the structure. So if we look at the left side, you can see the load is triangular, and we have a reaction. The right side, a reaction also, but the load is trapezoidal. And trapezoidal loads, although not hard, are more work than a single triangle. So we'll do the left-hand side. So I'm going to do the left-hand side. I want probably just my reaction at A. So I'm going to redraw my diagram. Assume reactions AY, AX, and BY. So I'm assuming how my reactions are going to behave. And then I have the triangular load with an intensity of 4 kips per foot. I'm going to compute the concentrated equivalent force. Since it's triangular, it's just 1/2 base times height. I left off my base, my length here. So 1/2 base times height looks like it's going to be 36. You guys see that? So 36 kips. Now I want to find AY, so I'm going to sum about B, so I want this distance. And we know the centroid of a triangle is 1/3 from the largest end. So that should be a distance of 6 feet. So now if I sum moments about B, using right-hand rule as my sign convention, and make sure it's in equilibrium, this 36 kip force creates positive moment about B with a moment arm of 6. And then AY creates what? Positive or negative moment? Negative. AY and its moment arm is 18. So it looks like AY is going to be 12. Kips. So now I'm going to come back and I'm going to draw a free body diagram of this chunk of the beam, which I know is at some distance x. I know my AY force is 12, and I've got this triangular shape. At my cut surface, I've got positive shear, positive moment. What is the intensity of the load for a given value of x? Well, basically I'm going to have to write the equation for the loading. So here's my load. If you want to go back to basics, AX plus B. So A is the slope. What's the slope of this line? Rise over run. It's 4/18, right? Times X. And then what's B? What's the intercept? 0. So that's it. So I can rewrite that as, it looks like the smallest I can reduce it is 2x over 9. And you can see when x is 0, it predicts 0. And when x is 18, the equation predicts 4. So it works. So now I know that my force here, I'll just call it F. So now I know that F is what? 1/2 base x times height 2x over 9. The 2's cancel and it looks like you get x squared over 9. And of course the distance will be 1/3. So it's at arbitrary x, we'll take 1/3 of that. Now if you're working this problem on the exam on Tuesday and you get to this point and you think you've got it, well, you've got over half the problem done, in my estimation. So the rest now is just apply statics and actually determine the functions. So if I were to sum the moments at the cut surface that I just created here on the left side, make sure they're in equilibrium, right-hand rule for my sign convention, let's see what we get. So this internal moment is positive or negative in my calculations. Positive. This force is going to create positive or negative moment about the cut. Positive. So the force is x squared over 9, and the moment arm is x over 3. So don't forget force, distance. And then I get all the way down here to 12. What kind of moment does that create about the cut? Negative. So I get 12 kips times the moment arm of x. So it looks like my moment equation, to solve for the moment, is going to be negative x cubed over 27 plus 12x. And that will have units of kip feet. Did I do that right? Yeah. Can we check that? Do we know the moment anywhere in the structure? I think at x equals 0, which is at A, what's the moment equal to? 0. So you plug in x equals 0 and you get?
0.
Yes. Over here at B, what's the moment? That will be at x equal 18. It should be 0. And what do we get if you plug in x equal 18 here?
0.
Have I already checked that, or are you just assuming? 0. Excellent. I like that. So you feel pretty comfortable that that's the maximum moment. That's the moment equation. So let's come here and finish it up by summing forces in the y direction, assuming up is positive. And let's make sure they're in equilibrium. So in our free body diagram, let's see the shear is acting down, the force is acting down, and the force is x squared over 9, and then the reaction 12 is acting up. So that says that my shear as a function of x is negative x squared over 9 plus 12, and that will have the units of kips. Now one thing we can check right away is the derivative of the moment equal to the shear. I think if you take that derivative, you see it's the same.
Plus 12.
What's that?
Plus 12. Oh, never mind. I wrote it at the beginning. You wrote it at the end. Never mind. Sorry.
You wrote what at the beginning?
12. Negative b minus x squared over 9 plus 12. No, I wrote it at the beginning. Never mind. Don't worry.
Oh. So that's good. Do we know something about the shear? We know the shear at x equals 0. We found it, right? AY. It should be 12. What do we get when we plug in x equals 0? 12. Now we did not solve for by, but I think if you look at it carefully, you'll see it's 24. And hopefully our equation at x equal 18 gives us 24. And let's see, if you put an x equal 18 here, 24. Except it's negative 24. I messed up. The shear should be negative 24 on the right-hand side. And I think this equation will give you negative 24. Sorry about that. So that I got a lot of green check marks there. So I like that. That didn't take us too long. It took us 10 minutes. It's a very doable problem for the exam. Now, in terms of the original problem, shear moment diagram, what do we usually like to get from the shear moment diagram?
Max.
Max. Now, how can we find that? I'm going to slide this up a little bit, give me a little more room. Now, in this particular problem, we can use mathematics to help us out. We know that the slope of the moment diagram is equal to the shear. And we know that when this is equal to 0, that implies that the moment is either a max or a min. So, can we set this equation equal to 0? Yes, we can. So the shear equal to 0 is equal to minus x squared over 9 plus 12. So when you solve for that, oops. So let's see, I put that on the other side, and it looks like it's x squared is equal to 108. Take the square root of 108 and you get 10 point something. 10.4. So that means the maximum moment occurs at 10.4. So you just come back and say, what is the moment when x is equal to 10.4 feet? So come up here and plug in 10.4 cubed divided by 27 negative plus 12 times 10.4. What do you get?
I get a big number. I don't know if that makes sense.
How big a number do you get?
214.
Well, 10 cubed is roughly 1,000. 1,000 divided by 27 is like 300.
I squared it.
Oh,
It's 41.
I don't think it should. I think it should be like 300 something, 200 something.
291.26.
291.26. Anybody get that?
I don't know 66 now.
Well, you got to add the 12.
Don't forget to add 12 times x at 10.4. This term's going to come out negative, and it's going to be reduced.
Oh, I didn't put the negative in there.
Hopefully the moment will come out positive.
I get positive 83.14.
83.14. Anybody else?
that's right.
You got that? Okay, great. So 83.14, and that should be kip feet. And that's really all we wanted from the shear moment diagram anyway, was what's the maximum moment and where does it occur? What's the maximum shear in the beam?
12.
Well, if you go back and look at our two endpoints, it's positive 12 and negative 24. Which is the bigger of those two? 24. And it would occur here at B.
And 24 is the reaction?
24 in this problem is the reaction at B.
And you just look at it and negative that?
Well, I just did it in my head. When I found AY to be 12,
Yeah.
and the total force acting down was 36, and this had to be 24. Any other questions? All right. See you guys Tuesday.